This is Chapter 10, Magnetically Coupled Networks, Sections 3 to 4. The learning goals for Sections 3 to 4 are to consider the ideal transformer, a modeling component used to change voltage and our current levels and quite common in electric technology, and safety considerations, important issues for the safe operation of circuits with transformers for professional practice. Section 3, the ideal transformer. Here we have a schematic representation of the ideal transformer. A network on the left generates a voltage plus or minus V1 of t, producing a current I1 of t through N1 turns of wire, which are on a so-called magnetic core, material which has magnetic properties, whose cross-sectional area is A, and whose flux is phi. That flux then links a secondary set of N2 turns of wire, producing a current I2 of t with a resulting voltage V2 of t across the terminals. And notice the dot notation. As we learned in the earlier sections, the dots indicate the direction of current flow to be in the same direction as that of the induced voltages. For example, I1 flows in, and so does V1 of t have its positive terminal where it flows in. And likewise, V2 of t has its positive terminal where I2 of t flows in, and the dot indicates that. In an ideal transformer, we assume that no magnetic flux phi actually goes astray. That would be called leakage, flux leakage, and it means that not all of the energy will be coupled from the primary of N1 turns to the secondary of N2 turns. We know from the previous sections that phi1 is equal to N times phi, and phi2 is equal to N2 times phi, where phi is the overall flux, and phi1 and phi2 are the generated flux due to the number of turns. In other words, each turn generates phi flux, and if there's N1 turns, we have N1 phi total flux. So, writing the equations now in terms of that, we find V1 of t is equal to N1 d phi dt, and V2 is N2 d phi dt. We can cast them together, if you will, set them equal to one another and divide through, and we would get V1 over V2 is equal to N1 over N2, at least in the conceptual idea. So that's the first equation for an ideal transformer as a result. The secondary voltage V2 can be calculated from V1 if we know N1 and N2, and any other parameter can be solved appropriately algebraically. Writing our ideal transformer equations now, V1 of t times I1 of t plus V2 of t times I2 of t has to equal 0 and for energy conservation. Here we assume that the energy transformer is lossless and energy transfer is to the secondary circuit. Likewise, that results in that I1 over I2 is minus N2 over N1. Notice the reverse relationship, N2 over N1, but also the negative sign for the direction. That's our second ideal transformer equation. These are two very important equations that should be recorded in your notes. The circuit representation is not as shown at the top of this slide. Basically, it's a schematic representation, and we show it as two linked or coupled coils with an iron core in this case, indicating it's an ideal transformer, with N1 colon N2 indicating the number of turns. We can then write, based on that particular representation, the two transformer equations that we just developed, depending upon the manner in which we would like to treat the secondary current. Notice that in the panel on the right, lower right, I2 is flowing out, and therefore the ratio I1 over I2 is plus N2 over N1. So it all depends on the direction you would like to assume for the current. Even though the dot notation is indicated at the top on the left-hand N2 side, here we're assuming that I2 is flowing out. Since the equations are algebraic, they are unchanged for phasors. Just be very careful with the polarity as indicated by the signs. Let's consider the reflection of impedances. We have a network developing a voltage V1 with the polarity shown, and a circulating current in the loop or mesh I1, clockwise direction, an ideal transformer with turns N1 and N2, a secondary voltage of V2, and a loop current of I2 with a load impedance of Z sub L ohms. It is also known to be an ideal transformer with no losses. V1 over V2 is equal to N1 over N2, since both the positive signs for voltages appear at the dots, or the so-called dot notation. Likewise, I1 over I2 is equal to N2 over N1, since the current I2 is leaving the transformer. We discussed that in the last presentation. We removed the negative sign as a result. V2 is equal to Z sub L I2, that's Ohm's law. And making a substitution, we get V1 times the quantity N2 over N1 is equal to Z sub L I1, the quantity N1 over N2. Well, we know something about the currents and the representations, if you will. We know the representations for V2. That's how we got that side of the equation. And we know the representation for I2. That's how we got the other side of this linked equation now through the impedance Z sub L. Solving and substituting, we get V1 is equal to the magnitude of N1 over N2 quantity squared times Z sub L I1. And this allows us to consider what the impedance would look like to the primary circuit, where the current is I1 and the voltage is V1. Solving then for the ratio of V1 over I1, which is our definition for what the impedance looks like in the primary circuit, we get the quantity N1 over N2 quantity squared times Z sub L, where Z1, if you will, is the impedance in the first loop or mesh, and Z sub L is the load in the secondary, which is in fact known to now be amplified by the quantity N1 over N2 squared, as long as N1 is greater than N2, doesn't have to be, or reflected into the primary side. It could also be attenuated if N2 is greater than N1. So for future reference, let's pull up some terms that we've learned before. For complex power, we know that S1 is equal to V1 I1 conjugate. We can make a substitution for future reference, and this should appear in your notes. V1 is V2 and N1 over N2, and I1 is I2 N2 over N1 conjugate, if you will, in order to produce the complex power in the first circuit. That's the same as writing V2 times I2 conjugate, and since it is an ideal transformer with no losses, that would be equal to the complex power S2 as a result also. Let's define N as N2 over N1, the so-called turns ratio. Phasor equations then for the ideal transformer can be written this way, using the turns ratio little n instead of capital N1 and N2. So V1 is equal to V2 divided by N. I1 is equal to NI2. Z1 is equal to Z sub L divided by N squared. And S1 is S2, since it is an ideal transformer with no losses of power, even complex power. So here we have our first practical problem based upon these representations and equations that you should have in your notes. Determine all the indicated voltages and currents. We have a 120 volt 0 degree phase voltage source developing a current I1 through an 18 ohm resistor. A capacitor's reactance is minus J4. Going into an ideal transformer, notice that the turns ratio is 4 to 1, 4 being on the primary side, developing a voltage V1 at the dot shown. And we're going to at least write that V2 has that polarity because that's the direction of I2, even though the dot notation is shown at the bottom of the transformer. And the load impedance is 2 ohms in series with a reactance, an inductive reactance of J1. So N, little n if you will, is the turns ratio. That's 1 over 4 or 0.25. Let's reflect the impedance into the primary side to make the transformer essentially transparent to the user or the first circuit. That is, Z1 then would equal ZL divided by N, little n squared. Okay. Well, we're going to do that by first finding out what Z sub L is, of course, and then reflecting it into the primary circuit. Z sub L is 2 ohms in series with J1. So therefore, when we divide through by n squared, n of course is 1/4, n squared is 1/16. It actually makes the impedance look, notice it makes the impedance look larger. So Z1, the reflected impedance, is now 32 plus J16 as a result. I1 then can be solved since we have, quote, reflected the impedance and we only have now a single mesh circuit. It's 120 angle 0 divided by 50 plus J12. I've added up the impedances, and 18 plus 32 is 50, and minus J4 plus J16 is J12. And as we know by now, in order to do complex arithmetic, we convert the rectangular form to its polar representation, and we produce an answer for I1 as 2.33 angle minus 13.5 degrees. V1, which we don't know, but we can now solve it because we know both the Z1 and I1. V1 is a voltage divider based on 120 volts coming in and 2 impedances, namely Z1 plus the other impedance in mesh 1, which is the sum of 18 and minus J4. We'll call that Z2. So Z1I1 is equal to 32 plus J16 times 2.33 angle minus 13.5. Z1 over Z1 plus Z2 is 120 angle 0 times 120 angle 0 then, making a substitution. 32 plus J16 divided by Z1 plus Z2, which is 51.42 angle 13.5 as a result, times 120 angle 0, so it's 120. There is a degree of complexity here, of course, as we have polar forms and rectangular forms. We have to straighten that out a little bit. We can solve for V1, if you will, by having polar form representations. We get V1 is 83.36 angle 13.07. Be careful with the polarities, though, in the current directions. V1 is perfectly correct because the current I1 does flow in. But I2, though, is a contributor, is I1 divided by N, and that contributor is negative 4 times I1. The 4 comes about because of the turns ratio, the definition for what happens to the secondary current I1 in terms of the primary current, secondary current I2 in terms of the primary current I1, goes by the inverse of the turns ratio, and in this case with a negative sign because of the dot. So V2 then, the secondary voltage, which we're asked to find, is minus N times V1 because of the dot, or if you will, minus 0.25 times V1, and that's because the plus sign is opposite then. Plus sign is part of the problem solution for V2, but it's opposite to the dot. So we end up with minus 0.25 times V1, and we have to take that into account when we do the calculations. Here we have another learning extension with the voltage source of 12 angle 0, a current I1 flowing through a 2 ohm resistor, a capacitive reactance of minus J2, an ideal transformer developing a voltage V1 with the dots as shown, a turns ratio of 1 to 2, a secondary circuit having voltage V2 from the transformer but a 2 ohm resistor in series with the minus J2 capacitive reactance and a final 2 ohm resistor, and our target variable is the output across the 2 ohm resistor plus a minus V0. But we're asked to find, of course, the current I1 delivered by the source. Well, N equals 2 by definition. Let's reflect the impedance into the primary side, and again, that makes the transformer transparent to the user, and we can solve a single mesh circuit. So the reflected impedance Z1 then would be ZL divided by N2 squared. So that's what we're going to do, and that would be the voltage across those the ideal transformer called V1. So that's Z1 that we're going to now calculate and put across those terminals, and now we have a single mesh circuit. So Z1 is 4 minus J2 divided by 4. It's 4 because we've added the two impedances together. That's 2 plus 2. And of course the 4 comes about from the square of the turns ratio little n. In this case, n squared is 4. So looking into the impedance from the 12 volt angle 0 source, we get a sum of impedances. We get 2 plus 1 is 3. 1 comes from the Z1. And we get minus J2.5, which is minus J2, and also a contribution of minus J0.5, which comes from Z1. Series impedances. I1 then is 12 angle 0 divided by 3 minus J2.5. Voltages in volts, impedance in ohms, currents in amperes, of course, standard units. Providing the algebraic calculation of the complex numbers, we find that I1 is 3.07, angle 39.81 degrees, amperes. As a learning extension for the same problem, let's find V0. Let's find the current in the secondary, which is just a secondary mesh circuit, and then use Ohm's law to calculate V0. Well, the secondary current I2 is I1 divided by N. It's one of our transformer equations. So I2 is I1 divided by 2 is equal to V0 times 2 ohms times I1 over 2, which is I2. So our answer comes about from the calculation that we did get for I1 and the 2 ohm resistor as a result, which is the only impedance that we do need in order to find V0. In other words, the capacitive reactance does not contribute to the voltage V0 on the output. So I2 is 3.07 angle 39.81 as a result. And from I2, we should be able to multiply by 2 and get V0. In this particular exercise, let's consider Thevenin's theorem to simplify circuits using ideal transformers. Well, here we have a voltage source on the left who has some unknown voltage, but we'll call it VS1, with a circulating current I1 through an impedance Z1, which is then connected to an ideal transformer whose turns ratio is 1 to little n, or n if you will. And on the secondary side, with the dot notation as shown, we develop a voltage V2, circulating current I2, an impedance Z2, and a secondary source, V sub S2. We're going to replace this entire circuit drawn here in blue with its Thevenin equivalent. In other words, all the way up to the transformer terminals, ignoring Z2 and the secondary voltage source VS2. And if we're doing a Thevenin equivalent circuit, as you know, we need to find the open circuit voltage. I2 in this case is equal to 0, and I1 is equal to N times I2. So therefore, in the open circuit voltage case, I1 is equal to 0. That means that V1 has to equal VS1. That's the only way we can get I1 equal to 0. If I1 was not equal to 0, then we'd have a particular problem with the calculation. But in this case, it must be 0 because of the open circuit voltage. There's no circulating current required. And therefore, V1 opposes the source VS1, and V1 is equal to VS1 as a result. So V1 is equal to VS1, V2 is equal to NV1, therefore the open circuit voltage is NVS1. To determine the Thevenin impedance, we'll let the voltage source go to 0 and consider what happens at the terminals 2 and 2' as an open circuit case. And we want to find the impedance looking into the transformer from the right. As shown here, we'll call it ZTH. So that really means that for the first time, we're going to reflect the impedance now into the secondary in order to find ZTH. So ZTH then, according to our ideal transformer law, would be N squared times Z1. So the circuit then now has been reduced to this circuit, where we have removed the transformer and replaced it with a Thevenin equivalent circuit to the left of 2 and 2'. And that circuit is NVS1 in series with N squared Z1 connected to 2 and 2'. And we now have a voltage V2, which is NV1. We have a circulating current I2, which is I1 over N, a voltage source V sub S2, and an impedance Z2. So one can also determine the equivalent circuit at 1 and 1 prime. It all depends on how the problem is focused in order to solve for different variables. So let's use Thevenin's theorem and reflect into the primary. Here's our same situation as we've had before in the previous slide. Let's find the Thevenin equivalent of the other circuit. Before we did 2 and 2 prime. Now we're going to find the Thevenin equivalent looking into 1 and 1 prime. In the open circuit then, in similar reasoning, we would find that I1 is 0 and I2 is equal to 0, or VOC would be VS2 over N. The Thevenin impedance will be the secondary impedance now reflected into the primary circuit. ZTH would be Z2 divided by N squared as a result. So our circuit then looks like this. If we now reflect into the primary, we get VS1 in series with Z1 across 1 and 1 prime. That voltage V1 would be V2 over N. We'd have an impedance Z2 over N squared, with circulating current I1 being equal to NI2, and a voltage source VS2 over N. That's the equivalent circuit being reflected now into the primary. The equivalent circuit reflecting into the secondary would look like this. They're similar but not the same, so it all depends on where you would like to take the reflection. Reflecting into the primary circuit or reflecting into the secondary circuit, as we've seen. So draw the two equivalent circuits for this particular network. We have 12 angle 0 in series with 4 ohms, a capacitive reactance of minus J3, circulating current of I1, a voltage V1 across an ideal transformer whose turns ratio is 1 to 2. Notice the dot notation that will come into play. A secondary circuit then consisting of 12 ohms in series with the inductive reactance of J4, circulating current of I2, notice the direction shown, as clockwise, and a voltage source as minus plus 48 angle 30 degrees. N is equal to 2, little n is equal to 2. We can take an equivalent circuit reflecting into the secondary. This particular circuit is drawn this way. You should put in your notes, especially for quizzes, because it's already a solution that we can use to solve problems. So we'll reflect the circuit into the secondary as a result, and we'll follow these particular rules in doing that. And we get this particular result as a result. Notice that Z1, which was before 4 in series with minus J3, is now by the turns ratio 1 to 2, and its square, which is 4, it's now 16 in series with minus J12. And we, of course, have voltage then V2. And then our secondary circuit remains the same, 12 and J4. And our voltage source the same also. If we reflect this circuit into the primary, we have this particular circuit. This should be in your notes and how to apply it. And this is what the circuit then looks like. Notice that the impedance in the primary circuit remains 4 minus J3. And in the secondary circuit, it has been reduced by N squared being 4. So 12 ohms becomes 3 ohms. And J4 divided by 4 becomes J1. And we have a voltage source then 24 angle 30 degrees. But in this case, we've changed the polarity of that voltage source because of the so-called dot notation. All right, so here's our learning example now, like a problem on an exam or a quiz. We have 24 angle 0 in series with 4 ohms, a shunt or parallel capacitive reactance of minus J4. Then that circuit continues with a voltage source of 4 angle minus 90 degrees in series with a 2 ohm resistor as the input to an ideal transformer with the dot notation and V1, turns ratio 1 to 2. And the secondary with the dot on the bottom and V2 is shown with a 2 ohm, a J3 inductive reactance, and a 2 ohm resistor across whose output will be measured as V0. To compute V0, since that's what we want, if we were to reflect the secondary into the primary, V0 would disappear. So it's better then to reflect into the secondary, and that will give us V0 as a maintained parameter that we can solve for. Before doing that, it's probably better to simplify the primary using Thevenin's theorem as a result. So let's get the Thevenin equivalent circuit of everything right on up to the transformer, and we can do that as a separate calculation. We would then have 24 angle 0 with 4 ohms minus J4, a voltage source of 4 angle minus 90, a 2 ohm resistor going to an open circuit voltage, and this open circuit voltage is the Thevenin equivalent voltage that we need to find. So that's the same as the voltage across this capacitor, whose reactance is minus J4. And in fact, the other voltage source, 4 angle minus 90, and the 2 ohm resistor has no current through it. So we'll consider that when we solve for VOC as a result. First, let's find VD, this voltage. That we do by a voltage divider, and then we would find that the open circuit voltage, since there is no current, would still have a contribution due to the 4 angle minus 90, which would be opposite in sign to VD. So VOC would be VD minus 4 angle 90 degrees. There's no current through that open circuit, of course. VD we find by voltage divider, the voltage of its impedance minus J4 divided by the sum of impedance, 4 minus J4, multiplied by the input voltage, which is 20 angle 0. We can straighten this out a little bit, if you will. You can divide through by 4, for example, and then find the particular calculation as a complex algebra problem. And as a result, we would get a solution for VD. We can then solve for VOC, VOC, which is 14.47 angle minus 33.69. Often there are mathematical steps that are skipped. When you look at these particular problems, you should do them to verify that you can do the complex algebra calculation and produce the same results. For the Thevenin equivalent circuit, we also need to find ZTH, and you do know that for ZTH, both voltage sources become short circuits. So as a result, we would have a 2 ohm resistor looking into those terminals in series with, that's the plus sign, 4 in parallel with minus J4, because the 24 angle 0 becomes a short, and 4 ohms becomes in parallel with minus J4. And therefore, ZTH can be calculated. Again, just a problem in complex algebra. And we would get ZTH is 8 minus J4 divided by 2, or if you will, ZTH is 4 minus J2. So this equivalent circuit is now transformed to the secondary through the transformer so that we can continue the solution. We know the open circuit voltage and we know the Thevenin equivalent impedance. So here it is. This is our solution from the previous learning example, including the Thevenin equivalent open circuit voltage and the Thevenin equivalent impedance. And we've ported that all the way up to the ideal transformer on the primary side with a turns ratio of 2, of course. Since we're now reflecting this circuit into the secondary, we will call up from our notes the representation of the secondary circuit analysis and apply it here. And the secondary circuit analysis would then reflect the primary to the secondary. So what used to be 14.42 is multiplied by little n being 2, is now 28.84. The angle does not change, though, because n is a real number, and when we multiply a polar number by a real number, only the magnitude changes, but certainly not the phase angle of minus 33.69 degrees volts. However, the impedances in that first circuit, Z1, are multiplied by n squared, which is 4. That's how we got 16 and minus J8. We have now removed the transformer and replaced it by a 2 ohm resistor and a J3 inductive reactance, which is what it had originally, and then in parallel with a 2 ohm resistor, which then provides V0. V0 then can be found very easily by voltage divider. In this case, by a voltage divider notation, it would be minus 2 over 20 minus J5 times 28.84 at an angle of minus 33.69. It should be noted that the voltage source has changed sign. In other words, the positive sign of the voltage source in the primary is now on the bottom, used to be on the top, and that's because of the dot notation on the ideal transformer. If the dot notation were on the same sides, it would not have changed sign, but in this case it does, and that's how it picked up a reversal, if you will. So therefore V0 now has a negative sign in it as a result. Doing the calculation in complex algebra, we can produce a result for V0 as a result, by manipulation correctly, hopefully. Here's another learning example extension. Let's find the current I1 in a primary with a voltage source of 36 angle 0, which is then flowing through a 2 ohm resistor, a minus J2 capacitive reactance, an ideal transformer with the dots on opposite side. We know what that means. A turns ratio of 1 to 2, a 2 ohm resistor, and a output voltage source of 12 angle 0, and we're interested in the current flowing in the first circuit, I1. Well, if that's what we want, we don't really need the secondary circuit because that's not where the target variable I1 is located. So let's reflect the secondary circuit using our preconceived notion into the primary, and we know how to do that because we know little n is equal to 2. And the circuit then would look like this as a result, removing what seems to be the transformer and replacing it by the equivalencies, if you will. 36 angle 0, Z1 is 2 minus J2, Z2 over N squared. In this case, there's only a 2 ohm resistor, so we end up with N squared being 4. 2 over 4 is a half. And the voltage source, V sub S2, 12 angle 0, has been reduced by N also. And that becomes 12 angle 0 divided by 2. Again, real numbers only change the magnitude and not the phase angle. And note the position of the dot marks. The position of the dot marks in this case are in support of the voltage source. So we get 12 angle 0 divided by 2. And therefore I1 is 36 angle 0 plus 6 angle 0 in this case, because we divide by 2, divided by the total impedance, which is 2.5 real minus J2 for I1, or 13.12 angle 38.66 degrees. Another similar problem, let's find V0. We have a 12 angle 0 source, 2 ohm resistor minus J2 ohm capacitive reactance, 1 to 2 transformer. Notice the dots are now on the same side. We have 1 to 2 turns ratio, little n is equal to 2. We have 4 angle 0 degrees, a voltage source, and a 2 ohm resistor, which establishes V0. So the first thing to ask is, where would we like to reflect the circuit? And the answer goes by where the parameter that we're interested in is. We're interested in V0, so we would want to reflect the primary circuit into the secondary. So that's what we're going to do. We're going to transfer the primary circuit into the secondary with little n is equal to 2 and take the analysis from that point as a result. Well, Z2 in this case can be rewritten if you want as a 2 ohm resistor, and VS2 as a result is still 4 angle 0. We have n times Z1, n squared times Z1, and n VS1, if you will, for the sources. So we have 8 minus J8, because n squared is 4. And the source here is n times VS1, so it's 2 times 12 angle 0, or 24 angle 0 as a result. But the voltage that we wanted to find, we're just casting it in this form because it really doesn't matter whether we put the resistor to the right and down or to the upper across. The voltage we want to find is still the target variable. It's the voltage across Z2, which in this case is plus or minus V0 as a result, the 2 ohm resistor. So V0 can be found by looking at the circuit itself and calculation of the circulating current and the circulating or the total voltage drop. So in this case, we'll consider the total voltage drop. Now look carefully at the polarity, and we'll do a voltage divider here for the total voltage. Look carefully at the polarity and you'll see that 24 angle 0 is opposed because of polarity by 4 angle 0. That's why we get 20 angle 0 as the voltage source. And we're doing a voltage divider, and the target variable is 2 ohms, so it goes in the numerator. And the sum of the impedances is then 8 minus J8 in series with 2. And that would be our equation for V0. Or V0 can be then calculated by complex algebra form, and we would get our result. Here's an interesting problem, a diversion. We have an ideal transformer, but notice the connections now. Notice that there is a 2 ohm resistor bridging the transformer and a short across the bottom 2 legs of the transformer. So we don't get separated circuits as a result, and we have to analyze this as a new departure. We have 10 angle 0 as a voltage source, a 2 ohm resistor going into terminal 1, an ideal voltage source of 1 to 2 turns ratio. Notice the dot notation producing the voltage as V1 and V2, always important for polarities. But we also have a 2 ohm resistor bridging terminals 1 and 2 across the top and a short across the bottom, and a load impedance of inductance whose reactance is J2. Nothing can be transferred. We don't have this as one of our models. That short across terminals 1 and 2 means that we don't really have this as one of our transformer equivalent circuits. So we're going to use the transformer equations and other circuit analysis tools. In electrotechnology, we often get problems that appear different, and this is certainly different from what we've been doing. Well, little n still is equal to 2. That doesn't change. So the phasor equations for the ideal transformer also don't change. The voltage V1 is V2 over little n, and the current I1 is equal to n times I2. And because of the dot notation, we have that particular representation. We now have to look at currents leaving a node, and here are the 3 currents that are leaving that node at node 1. At node 1, we would get the currents leaving the node would be V1 minus 10 angle 0, because there's 2 voltages across the 2 ohm resistor, so it's V1 minus 10 angle 0 divided by 2. That's one current. Another current would be V1 minus V2 flowing through the 2 ohm resistor, which bridges the terminals 1 and 2. And the other current is I1 is equal to 0. There are also 3 currents at the second terminal, 2. We would get V2 minus V1 over 2 ohms as one of the currents. We'd also get V2 divided by J2, which is the current that flows through the inductive reactance. But we'd also get minus I2 because we have assumed that I2 is flowing in because of the configuration of the transformer. So therefore, it's minus I2 equals 0. 4 equations and 4 unknowns. Well, here are the 4 equations straightened out and rewritten. We can substitute into the equations because they are a set of equations, therefore they all are valid all at the same time. V2 is equal to 2V1. We can do that, and we can solve for the only unknown for that one equation as a result. V2 is equal to 2V1, and under those conditions, we would get 0, very interestingly. And under those conditions, I2 can be solved because V2 minus V2, I2 V1 minus V2 is going to be essentially 2V1 minus 2V1 is 0. So therefore, we can solve for I1 as 5 angle 0. It's kind of fortuitous and doesn't often happen that way. I2 then can be found, since we found I1. I2 is equal to 2.5 angle 0. We can then take the second equation and make a substitution as a result and find an equation then where we've eliminated I2. And we can also eliminate V2, and we get this particular equation. And therefore, we can solve for V1 as square root of 5 angle 63.43 degrees, when V2 is equal to 2, the square root of 5, 63.43 degrees. Now, my comment here is that first fortuitous substitution, which removed the variable from the first equation, is only because of the way the problem is set up. So it doesn't often happen. 4 equations and 4 unknowns, though, can be solved by matrix manipulation, but that's a little bit more complicated. We have a problem-solving strategy. I'm going to let you read that yourself. It's in the textbook also, for circuits containing ideal transformers. And if you didn't have enough time to finish the reading, it's in the text, and please read it carefully. But those are the functional steps that we've been developing. This is Chapter 10, Magnetically Coupled Networks, Section 4, Safety Considerations. These are a variety of technical discussions which are not really circuit theory, but are useful for your professional understanding. Here we have 2 houses fed from different distribution transformers. There was a problem in one house in which the utility company circuit breaker has opened the line, and house B essentially has now gone dark. Notice that the line voltage is very large, 7,200 volts, but the transformer steps it down, for example, for house A to 120 volts for distribution. Your good neighbor is not so good in this sense because your good neighbor runs an extension cord, and you're now powering house B throughout the entire house at 120 volts by plugging an extension cord with live voltage into a receptacle. This is not very good practice at all, because what happens is that second transformer now on the pole has excitation, and when a power company worker or technician works on that pole, instead of finding 0 volts, he will now find 7,200 volts. He didn't expect to find any, and if he was probing around thinking that it was a circuit with a problem, he would actually find it has 7,200 volts. So this is not good safety practice. So why high voltage transmission lines? Why do we do that? Why do we have such high voltage transmission lines? Let's do a case study in which we're going to transmit 24 megawatts over 100 miles with 95% efficiency at 2 different voltages, 240 volts and also at 240 kilovolts. Remember that power is 24 megawatts. A given conductor's resistance can be calculated R as rho L over A, where rho is the resistivity of the material. For example, copper is 8 times 10 to the minus 8 ohms per meter, relatively good conductor. L would be the length of the conductor. In this case, 100 miles would be 160.9 kilometers, or if you will, 1.609 times 10 to the 5th meters. And A would be the cross-sectional area, which would be pi r squared, of course, for a circular cross-section. The maximum power loss, though, is 5%. So the maximum power loss would be 24 megawatts times 5%, or 0.05. That means we are supposedly losing 1.2 megawatts in our transmission. The known line losses, though, are due to the resistance, so the losses are also equal to Ri squared. At 240 volts, though, we need a current I of 240 megawatts divided by 240 volts. Remember, volts times current is equal to watts, or 10 to the 5th amperes. We would need 10 to the 5th amperes to flow. And as a result, we would have 1.2 times 10 to the 6 watts dividing through is equal to 2 times 8 times 10 to the minus 1. We're calculating the resistance times 1.06 times 1.609 times 10 to the 5th, which is the length, divided by the area, which is pi r squared, times 10 to the 10th. Well, this is the problem, because producing this calculation where the voltage is 240 volts, we find that the copper conductor will have a radius of 8.6 meters. That means a diameter of twice that. That's a very large piece of copper as a result, and very heavy and totally impractical. If we up the voltage to 240 kilovolts and do the same result, we find that I sub L is 10 squared, down from 10 to the fifth. And if we calculate again the power loss in terms of the necessary radius to support that, we find that the radius has now dropped from 8.6 meters to 0.86 centimeters. Much more reasonable result. It's less than 1 centimeter radius, less than 2 centimeters overall diameter. So that's why we transmit at very high voltage, any given power level. In this learning example for professional interest, let's rate a distribution transformer. We have a utility substation providing 13.8 kilovolts to a local step-down transformer. Usually they appear on your power poles out front, and they can provide two 120-volt circuits, or if you will, by going across the transformer, one 240-volt circuits. Households are in fact wired in parallel across this local step-down distribution transformer, and usually up to 10, and the maximum current per household usually is 200 amperes. Let's determine the step-down ratio that we need, little n. Well, V2 over V1 is little n. So substitution of the numbers, 240 volts, which is the overall secondary voltage, divided by 13,800 volts, or 13.8 kilovolts, we get a step-down ratio, little n, of 1 over 57.5. Let's determine the power rating. The maximum secondary current, because we said there were upwards of 10 households that could be connected to this transformer, would be 10 times 200 amperes, or 2,000 amperes. And we also know that N is I1 over I2. We know what N is now. So therefore I1 is 2,000 divided by 57.5 actually, or 34.78 amperes, if you will. Therefore the power that this transformer is asked to consider would be 13,800 volts times 34.78 amperes. Notice the current on the primary is less than the current on the secondary. Secondary current's 2,000 amperes, and the primary current's only about 34.78. But the overall power of this transformer as a result is 480 kilovolt amperes, Since it's not resistive and a loss, it's measured in volt amperes, VA. We also know that power is 240 volts times 2,000 amperes on the secondary side, and that it was the same result, because this is assumed to be a lossless transformer. Here's something that is becoming more and more prevalent, that is contactless charging using mutual inductance. So you have a secondary circuit, could be a toothbrush with a rechargeable battery, could be a cell phone, and you have a power station, if you will, which has a coil on it, and you bring the item, the consumer item in question, close to the cradle so that the two coils are in fact coupled to one another, and we get a transfer of energy using transformer action. And that's our transformer circuit, if you will. So we can have V1s, could be, for example, 20 angle 0 RMS going into an inductor J omega L1, which represents the transformer. J omega mutual inductance, this is what we considered in this chapter, first couple of sections. Secondary transformer J omega L2, current I2, and a battery voltage then, which is going to be V2, a sinusoidal voltage, which will then be converted by the battery charger using rectification, semiconductor diode, for example, into a DC charging voltage for the rechargeable battery. V1, as we know from this chapter, would be J omega L1 I1 minus J omega M I2. Look at the dot notation for that, and we find V2 is J omega M I1 minus J omega L2 I2 because of the dot notation. We also know that L2 is equal to alpha squared L1. V1 is equal to J omega L1 minus J omega K times alpha L1, I1, where K is the coupling factor, of course. And we've now introduced the coupling factor, in this case 0.5 as a number, into the equation. And V2 is j omega k alpha L1 I1 minus j omega alpha squared L1 I2. V1 then is 120 volts RMS, and V2 is supposed to be on the order of 6 volts RMS. We can form ratios, if you will. 120 over 6 is 20, and we can set them equal to the ratios of V1 and V2 using our coupling factor K and our efficiency alpha. We can assume that the currents are in phase so that we can do the calculations not as phasors but as just magnitudes, which is what we've done here. We could then calculate what alpha could be, or should be anyway, as a result. Well, it turns out that alpha is equal to 0.246 then divided by 1.02, and therefore L2 is equal to alpha squared L1, and L2 would be the smaller of the two inductors as a result. We can then solve for V1, assuming the currents are in phase again, just to make the numbers easier to do, and we get V1 is equal to 0.494 omega L1. Depending upon what frequency we run this at, we would get different values of L1 as a result. 60 hertz would be common if we ran it from utility. We would have 693 millihenries. If we ran it from a higher frequency source, which can be converted from 60 hertz through a switching device, either at 20 kilohertz or 100 kilohertz, we can drop the amount of the inductance that we would need as a result with the higher frequency, because it is a function of omega. So, battery charger with a high frequency switch. Just for professional interest, we have 170 cosine omega t, 377t, developing a current I1 into a transformer with L1, L2, and mutual inductance. An I2 circuit developing a voltage V2 for the battery charger. And we have a switch which is closing and interrupting itself about 100,000 times a second, 100 kilohertz rate. We can now consider induced electric noise as a result. That's another possibility of what could happen when we have a charging circuit. Here we have 340 angle 0, producing a current 5 angle 0 through j omega L AC, if you will, to an AC load. The coupling factor K is equal to 0.5 to a secondary circuit, which has a 5 volt DC source with an inductor and a DC load. So the question becomes how much of the AC is actually being coupled to the DC, which would then induce a noise on the secondary DC load, usually the desirable load. Well, the voltage that appears in the noise would be j omega m, the mutual inductance, times IAC, the current flows in the AC circuit, and that's a function, of course, of the coupling factor K, as we saw from earlier in this chapter. So that's j omega k, the square root of LAC in the AC circuit, times LDC in the DC circuit, and then multiplied by IAC, the current that flows in the AC circuit. Putting in some values, for example, 10 nanohenries for LAC, we can calculate V noise then. In this particular representation, we'll take V LAC and LDC to be 10 nanohenries. We'll take K equals 0.1. And we find that the induced noise, V noise, voltage noise, is 3.14 times 10 to the minus 8th, but it's multiplied by the frequency F in volts. If we have 60 hertz, then the noise turns out to be relatively small, 1.88 microvolts. If we have an FM radio transmitter, we can increase the frequency from 60 hertz up until the FM broadcast band, which is 100 megahertz. At 100 megahertz, that's 10 to the 8th hertz, so F would be 10 to the 8th, and the noise turns out to be a whopping 3.14 volts, which would ride on top of a 5 volt DC source and would certainly not make the DC load extremely efficient, and it would be subjected to quite a lot of noise. This is a type of device called an LVDT, a linear variable differential transformer. And it's a device for measuring displacement. So the movable magnetic rod is connected to some device like a conveyor table or something like that where you will want to measure displacement. We have a primary coil and a secondary coil shown in the split view on the left. The circuit has a Vin of about 10 volts RMS, a frequency of 2 kilohertz, and we have LP, the primary coil, and we have two secondary coils, LS done twice essentially. And as a result of having two secondary coils which are separated in space, we have M12 and M13 as a result, producing the secondary current I sub S at a voltage V0. Here's what would happen through an experimental result of the different values of the coupling capacitor and as the device actually travels. So what you do get is you get an output then, the coupling coefficient, as a function of the travel as a result. And therefore, we can measure displacement by having some linear representation over some range. Sometimes that's hard to do, as you can see by the blue and the red lines. And we get an equation then for Vin, which can be written as j omega LPIP plus j omega M13 I sub S. But because of the dot notation in the lower coil and the upper coil, we get minus j omega M12 times I sub S as a result in terms of V0 and Vn. So adding V0 to the mix, we get an equation now on the secondary side, which is written this way, two equations now, from which we can get Vn is equal to j omega LPIP, and V0 is equal to IP j omega, the quantity M12 minus M13. The concern is that this is with no load or open circuit, and usually that can be done by making sure that you have a high impedance device like an operational amplifier actually measuring the voltage. Or V0 then, under no load conditions, becomes Vn the square root of L sub S over LP times the quantity K12 over K13, and you'll notice from the graph that K12 and K13 have different values depending upon the displacement or the travel. So that's how we would get an output voltage, which would tell us what the displacement is. Typical values, for example, K12 minus K13, the magnitude would be 0.8. We would get V0 approximately equal to Vn, and we would have values then for LS over LP, which can then be calculated. The ratios can be calculated. LVDT continued, considering what we just described. For a no-load condition, we would get V0 is equal to Vn, the square root of L sub S over LP, K1 minus K2. Here we'll take LS over LP to be 1.25 squared, or 1.5625, if you will. And we have our values for K12 and K13 over different ranges. Substitution, completing the analysis, again assuming zero phase input, so we can do it rather from any other considerations, but just from zero phase input for Vn. In other words, Vn has a zero phase. These are the processing equations that we would get for different values of travel of the LVDT device. Or Vn is equal to j omega LPIP. There are design equations for the inductances, and a typical example might be IP would be 10 milliamperes RMS, Vn would be about 10 volts RMS at a frequency of 2000 hertz. So we would be able to calculate then what LP would have to be, because we know what Vn has to be in IP, target variables. LP would be 31.8 millihenries, and L sub S would be 49.7 millihenries. In this learn by design problem, we're going to use a 100 volt to 12 volt transformer to build what's called a 108 volt auto transformer. And we'll describe what that is when we consider it. So a conventional transformer has two turns, N1 and N2, on a common core, and the core is there to link the flux flowing in one circuit with the output in the second circuit. We can then, though, hook up this particular circuit this way, If it is a 120 volt to 12 volt transformer, we can come in with 120 volts from our utility line input. We can connect that to the 120 volt winding. Let's call it the N1 winding, which would be V1 then, showing 120 volts RMS. The secondary would develop 12 volts, of course, and if we wire the secondary in series with one of the terminals of the primary, we could do so by picking the proper dot notation. See, V2 has 12 volts RMS, but the dot notation is on the bottom, and V2 is equal to minus plus. So V2 would actually retard V1 or reduce V1 to 108 volts RMS. And the concept here is that maybe the Christmas lights won't burn as bright and they'll burn longer. So the auto transformer connections can be done in a couple different ways. We can add them together. For example, if we do that, we would get the sum of the voltages. Notice the dot notation means that we would get the sum of the voltages. We'd get 120 plus 12. Or if we wire it the way we just described, with the dot notation the way we just described, that's a subtractive connection. So we can get, in this case, 108 volts RMS. And those, of course, are the processing equation that results, and those signs result because of the dot notation. In the additive connection, we have N1 and N2, and in the subtractive connection, we have N1 and N2, but it's the dots that have been reversed. Use the subtractive connection then on the 120 volt to 12 volt transformer to produce our target variable of 108 volts. It's called an auto transformer because there is no functional primary and secondary. It's sort of all primary, essentially, although there is a load across the device. This is the design of an adapter or wall transformer for consumer applications. We have a voltage source V1 at 100 angle 0 volts RMS, secondary circuit producing V2 volts, an AC to DC converter whose output is nominally 9 volts, but there is a controller that monitors the output and provides a feedback signal, hopefully keeping it about 9 volts. Our design constraints are that the power delivered by the DC output would be less than 2 watts. V2 is going to be greater than 12 or so, and eta, the efficiency, would be 0.6. The transformer turns ratio we can analyze. We'll just come in and put some safety numbers in here for the different voltages, and that equation is actually wrong. It's V1 over V2, but we get the transformer turns ratio is about 12.6 as a result. We can take a safety margin, if you will, and make it a little bit bigger by just using that as a base value and then working in this desirable margin. P in over P out is P out divided by eta, the efficiency, or about 3.33 watts. And therefore I in was P in divided by V in, about 27.8 milliamperes RMS. And we can specify a 100 milliampere rating to give us even more of an extra margin. That is the end of Chapter 10, Magnetically Coupled Networks, Sections 3 to 4.